Nick Hensel from Fairport High School and is advised by Dr. Jacobs Perkins. And Nick is going to talk about high-speed measurements of target support vibrations using line scan cameras.
So, over the summer, I used line scan cameras to measure target vibrations. And this picture I have here is a setup that I've been using to image a target stock using a line scan camera that is mounted on a shaker table, which is excited by this shaker. It acts roughly like a speaker coil and vibrates back and forth based on some sort of input current, and is illuminated by a blue LED that is controlled by a trigger that was designed by another scientist here at the lab. So, to validate the use of this line scan camera for measuring target vibrations, I have to go through 4 steps. I have to identify the problem and justify the needs for the cameras, generate test images, develop and apply image processing routines in MATLAB, and then analyze data taken from those images. So, what is a line scan camera? A line scan camera is fundamentally different than an area camera. So an area camera takes a 2-dimensional image, and shown here is the pyramids of Giza. However, a line scan camera will take one line from that image and display it many times unless it's moved, so it changes the field of view. So a line scan camera would show time and position as a function of time instead of a 2-dimensional image. So here's a video of the fusion target from the laser bay prior to the experiment, and it was taken with a traditional high-speed 2-dimensional camera. And this is the target vibrating inside of the target chamber. And if this was taken with a line scan camera, it would look very different. So, why do we care that the target is vibrating? Laser fusion experiments are extremely sensitive to target vibration. So you've got this target that you just saw mounted on 4 spider cells suspended on a target stalk. And that target vibrates back and forth. But if that target vibrates more than 20 microns, or 20 times 10 to the negative 6 meters, from target chamber center, then it will greatly reduce the effectiveness of any experiment. So we have to find out why that target is vibrating, try to isolate what frequencies it is vibrating at as a result of background machinery, and limit that vibration. So cameras are useful in capturing these target stock vibrations because they are non-contact forms of measurement, unlike accelerometers, which require contact with the target because they measure accelerations based on contact. Cameras also easily measure the displacement of the target, which is what we are concerned about. And line scan cameras, with one shown here, are much less expensive than traditional 2-dimensional because they're $900 rather than $25,000. So here's a simulation of viewing the target, or this red circle, with line scan cameras. So if you imagine you have 2 views of the target with 2 line scan cameras at the top and bottom, and then we look at one of those views. If you take images of that target as it moves, this is what it will look like in a transverse axis. It moves back and forth, and you only see that one sliver of the target. So that's action 1 showing the transverse movement of the target. Additionally, you can show vertical movement based on how wide that band of the circle looks over a period of time. So you can additionally measure up and down motion of the target based on the thickness if you're imaging a circular or a spherical object using one single camera. Now, if you were to take the images gathered from that moving circle and plot them over a period of time as it moves back and forth, you would generate this back and forth movement. So you have displacement as a function of time, graph as an image. And if you take multiple cameras and synchronize them and have them image this target, you will be able to construct a 3-dimensional movement because one target captures that up and down movement and side to side, and the other additionally captures up and down movement, but because it is placed orthogonal to the first camera, it also captures movement along the other axis. However, if these cameras are not synchronized, then the data you collect will not be useful because you cannot plot it in 3-dimensional space because they are not linked in movement at the same time. So this controller was created to synchronize light sources that illuminate a target with 3 cameras that are imaging whatever target you're looking at. And that controller has some line clock which controls how fast the LEDs and cameras are capturing images. And the line clock can be somewhere from 500 to 4,000 hertz, and that dictates how many lines the cameras collect per second. And as a pulse width, it dictates how long each line is collecting data. And the longer the pulse width, the more light you will collect, but the more blurry you will have with each image. So to test the image properties and the ability to collect images of the landscape camera, first I generated a sine wave within MATLAB, and then plotted that image using a program to turn it into an image that had 50 pixel width, and wrapped it around a cylindrical drum, and I put that drum on a motor and spun it. And I created images by spinning that drum, capturing that movement while illuminating with a laser. And the problem with this image from here to here is that it's not magnified significantly. It's not a continuous graph. There are points where it jumps when it didn't continue to collect the right points of data on that spinning cylinder, and it's an uneven source of light, so it will be difficult to extract data from the target. So the third setup I used was that electrodynamic shaker I showed you at the beginning, and I had some target that I was viewing with the camera that was being illuminated by an LED, and it is a much larger target because it was magnified to a much larger resolution, so that each pixel on this target represents 3.83 or approximately 4 microns of actual space. And this image is much more reliable because it is continuous, it's very evident where the target is, and it has a significant magnification, so it's easy to see where everything is. So finally, to process these images, you first have to read them in, crop them to the area of interest, then use a spline interpolation to create subpixel resolution and increase the virtual qualities you have with that target. Convert that image to binary, and then extract data points from that image using edge pixel finding. So first you're going to crop to the area of interest where you have movement, and then you will use a spline interpolation to basically spread out the data in each line, and the aspect ratio becomes distorted because you are creating subpixel resolutions that can't be displayed in an image, so it has to stretch it when it's actually displayed on the screen. Then you take the interpolated image and convert it to binary using some threshold value, so that anything below a certain brightness or above a certain brightness is not counted. So the values of 0 to 255 in this image, I took only values that go from 0 to 101.11 and said that those values are true and everything else is false, which creates this black and white image. Then, using an edge pixel finding routine, I find in each line where it switches from false background to the true foreground and plot that as a data point, which forms this graph. And then I centered it around the 0 point to show the oscillation. And here's an example of what the image would look like if I had not done that spline interpolation step earlier. And it has the blue is the interpolated image. It's much smoother than the red, which has a lot of peaks and cut-off areas where it has not been interpolated, so it's much longer. And this is the graph of the relevance of this camera. This is the most important element of research done with the cameras because it determines where this camera will actually be useful in terms of measuring the target. This black line represents the resolution of the camera. It's a 4 micron per pixel line, which means anything below this line will not be picked up by the camera because the displacement is not large enough that the camera will be able to see that it is happening. And so this graph shows that for some value of acceleration at some frequency, you will have some displacement. So if the target has a 1 g of acceleration, that's this red line, and it is vibrating at a very high frequency, you will have very small displacement. So this cutoff line shows that everything above this will be imageable by the target. So for a 1 g acceleration, the target has to be operating at less than 400 or less than 200 or so hertz to be imaged by the target, or imaged by the camera. And this is relevant because it shows where this camera will be useful in measuring actual target vibrations. And if there are very small accelerations, this camera will not be useful in measuring values that are less than some low frequency, because otherwise the displacements will be so minute that the camera cannot pick them up. So in conclusion, line scan cameras are only useful for analyzing vibrations when the displacement exceeds the optical resolution of the camera. So they are only useful in measuring when you have a low frequency oscillating at a high acceleration or has a high displacement that is greater than the optical resolution of the camera. And I would like to thank Dr. Douglas Jacobs Perkins for helping me when he could. He didn't expect to help me originally because of some problem at the beginning of the summer with my original advisor, and he stepped up and is willing to help me with my project. And Gerald Abt, who's a graduate student, he helped me with some routines in MATLAB when I needed assistance. And Dr. R.S. Gregson for running this program every year.